going to be in the break before the poster presentations. But yeah, we'll try to have a group picture with everyone. Okay, and then with that, we can start with the orals. So just a reminder, everybody gets 20 minutes. That should include questions. I'll start stopping people if they go way beyond that. And we'll start with the first oral. So Rafal, probably pronounced the name wrong. Rafal is going to talk about balancing expressivity and robustness, constrained rational activations for reinforcement learning.
So, hello, my name is Rafał Surdej, and together with my fellow colleagues from Warsaw University of Technology, Michał Bartkiewicz and Mateusz Ostaszewski, and also with Alex Lewandowski from University of Alberta and Claire Lai, who's together with us from Google DeepMind, we created this word named Balancing Expressivity and Robustness, Constrained Rational Activations for Reinforcement Learning. So first of all, I would like you to present a short introduction to the topic we are addressing. So let's take into consideration a single neuron model from a neural network. So as we all know, every neuron has its activation function. And usually this function is fixed, or sometimes I'll call it static, like ReLU, which means that it doesn't change. But what if we replace such function with the one that has trainable coefficients and can change its shape throughout the training? And specifically, we'll be looking at trainable functions, which formula is the rational function, which is the ratio of polynomials, and we have numerator and the denominator, and all A and B coefficients are trainable parameters that could be trained alongside network parameters. And why would we do this? There is recent work that proved that replacing a static function with trainable rational activations can really boost models' expressivity and plasticity in reinforcement learning. But there is also a danger, how would these unconstrained rationals would behave in more demanding continuous control domain, especially with a high update to data ratio, which means that for each agent step in an environment, there are multiple gradient updates of the network parameters. And also the original paper performed only experiments on discrete Atari action domain. So there is our research question: does the flexibility of rational activations is beneficial for the training in reinforcement learning, or it would harm its training through expanding existing problems like overestimation and gradient explosions? And actually, second option was the case especially in the MetaWord benchmark, which is continuous control reinforcement learning task. The rational functions that I will call now original rationals lead to severe instabilities. So there was a phenomenon which we called activation explosion, and that means that the activation function returns really large numbers for relatively small inputs. And this in case lead to huge critic overestimation and the complete collapse of a training process. So as you can see here. So what we wanted to do, we introduced some structural constraints to improve the rational trainable function stability. So basically, let's start from the original function. So the main change is the introduction of the term that has the highest degree to the denominator. And this term would cause the activation to decay towards zero the larger the input is, preventing the uncontrolled growth. And we also remove the constant A0 term from the numerator. And this ensures that the function passes through the origin, which is common with the most popular activations. And we empirically found that it's really beneficial. So this is what our new rational function looks like. It's basically in some interval that we say before the training, it behaves like a standard original rational function within this interval, and outside it slightly decays towards zero. And what are the results? We performed experiments in both DeepMind Control Suite and MetaWorld benchmarks with a soft actor critic algorithm, and results were as follow. So basically, the original rationals perform really poorly due to the instabilities that I mentioned before. Our constrained rationals really outperform those original rationals and are very close to the very strong ReLU plus parameter reset baseline, which performs really well across both benchmarks. But if we combine our constrained rational with periodic parameter resets, it achieved the best overall performance from all the setups. But with this performance, we revealed a kind of bitter trade-off. So basically, as you can see on this overestimation plot, some kind of constraints are really required for the stability in continuous reinforcement learning. But we also wanted to check how those constraints influence with the plasticity of a agent. So we created an experiment in which we tested our simpler neural network on the MNIST with reshuffle labels continual learning setup, which means that we have sequential tasks, and before each task, we take the MNIST dataset, we shuffle its label, and we try to train our agent. And basically, we find out that the very constraints that brought us this stability in reinforcement learning now causes that this network loses its plasticity much faster than original rational function. And to regain this plasticity, there is a need for some kind of another regularization, which we used weight decay and it restores plasticity. And we also wanted to analyze it, why such behavior happens. And first of all, we tried how different initialization of coefficient, like how the initial coefficients influences the performance of the agent. And what we found out is that the high magnitude initial coefficients were critical in reinforcement learning, especially in MetaWorld. But on the other hand, if we initialize the rational function with low values, it really helps to preserve the plasticity in continual learning setup. And we tried to explain this with neural tangent kernel function, which tells us how two data samples are similar to each other according to their changes done to network parameters after gradient update. So basically, if we take such function and calculate it on the whole batch of the input, then we can say how much information this batch contains if we look at it from the neural network perspective. And the high inits lead to higher NTK matrix rank, which means more expressivity through this, that this neural network covers more complex function space. And this helps for the stability in complex reinforcement learning tasks. But on the other hand, low initial coefficients lead to more constrained function space, and this helps to preserve the plasticity in continual learning. And also, we provided a deeper analysis at the role of weight decay, because we wanted to see why our constraints harm the performance on a continual learning setup. And what we found out, that's on the bottom left, throughout the training, parameters tend to have such values so that the activation flatten towards zero. So it returns are really small numbers, and which is very similar to neural dormant effect. And the neural network completely loses its responsiveness, and the training isn't possible. And if we apply the weight decay on the right image at the bottom, it acts as some kind of a regularizer, which prevents these drifts of coefficients, and is really beneficial for the performance and also the plasticity. But of course, it's not so colorful. And in reinforcement learning, this isn't the case, and such phenomena don't occur there. And if we apply a weight decay in reinforcement learning, basically it's too harsh, and the network loses its expressivity, and thus it collapses their performance. So basically, what are the key takeaways from our research? We identified a critical failure mode. The original unconstrained rational functions suffer from what we call activation explosion, and are not suitable for demanding continuous control reinforcement learning tasks. We proposed a constrained rational version of this activation function that ensures stability and improves the reinforcement learning performance. But on the other hand, we covered a trade-off between the stability and plasticity, and the properties that provides stability also causes the network to lose its plasticity in the long term. And we provided a deeper analysis, showed how this trade-off could be managed via other regularization methods. So the conclusion from this is, I personally believe that trainable rational activation functions have promising advantages, and could be really beneficial if handled properly. For now, the only thing we can say is that their design require careful consideration, depending on the use case we want to use them in. And for sure, there should be further explored in the future. And we provide some kind of possible destinations for the future works, like dynamic mechanisms for adjusting activation function expressivity throughout the training. So we could dynamically manage this trade-off between stability and plasticity. Also, it would be really beneficial to have some theoretical analysis on the inference on loss landscapes. And it would be really beneficial to explore them in different architectures and in maybe in different agents. So thank you very much. That was all.
He raised his hands early.
Thank you for the talk. I was wondering, like the constraint you introduce, you have some degrees of freedom in the polynomials that you can pick. So typically in a rational activation function, you would pick a higher order polynomial in the denominator than the numerator, which seems like if you maybe pick the very high order denominator, it might achieve something similar to the constraint you have introduced. So have you like played around with the degrees and like, or what were the degrees of the polynomials you've picked, and how did it influence your results?
Yes, we tried different degrees of the powers of the numerator and denominator, and actually, as the original paper, we had the same conclusions that the degree in the numerator should be slightly higher than the denominator, because otherwise it completely collapses the performance of the agent. And of course, it should be around only 1 power higher than in the numerator than the denominator, because otherwise this activation explosions effect tends to occur much faster. But we also tried really like many different like natural regularization methods, like only the weight decay at the coefficients, but none of this provide any like general result that could be applied to every scenario. Like basically, when something was better in the continual learning, it also tends to be worse in reinforcement learning. And only after applying those constraints that we showed, it was really we could really have the overall good performance.
Okay, thank you for your talk. I wonder, is the behavior you observed in rational activation only occurring in reinforcement learning, or it occurs in other types of continual learning as well?
No, we have tried. We have tried also continual learning on C4 data set and this MNIST data set, and none of such behavior occurred in continual learning. And it's even hard to say that the whole reinforcement learning introduces this instability, because like the Atari benchmark, there are no instabilities for this activation function. Only the continuous control task. And even I could say that the meta world is worse because it has the higher returns and higher gradients.
Okay, thank you.
Last